Hi and welcome back. We are exploring the Ethernet tonight, a little bit of review about the MAC sublayers, and then we're going to talk about how switches work, because switches are layer 2 devices, and we're all about layer 2 this week in chapter 5. So I'm going to slide away and then get going here. So the Ethernet protocol. First part of this, we're going to talk about the sublayers and frame fields, which we talked a little bit about, but I'll demo a few more things. And Ethernet and MAC addresses and how they work. So, one thing that we talked about the other day is that the data link layer is broken into two parts. The MAC, the media access control, which is MAC, and the logic link control, which is the data. Again, this is where the physical properties of a computer, the physical coding, the electronic pulses, the light pulses, coming in on various cables and media, get converted into logical processes that are used in the computing side. When we say it gets passed up to the upper layers, it happens at the data link layer. It takes it, strips off the MAC addresses, and hands the encapsulated data up to the application area. Ethernet's all over the place. It supports lots of different speeds, as you can see. It also does a lot of, supports a lot of different speeds, and so clicking a little much for you there. And it is also media independent. And it has, it's the most widely used in the world. Is it the most efficient or the fastest? No, it's not. But it's the one everyone uses because it's the most widely adapted. So on the MAC sublayer, we have physical sublayer signaling in the physical medium against, again, the cable. And these are all the different speeds that it accepts because it's just counting patterns of ones and zeros at different rates. The faster, when we say computers get faster, they're not so much getting faster, is our counting is getting better. We can count more and more data coming in and isolate it. And so that's what's happened over this evolution of time. So the media access control takes it and brings it up to the LLC, the logic link control sublayer. So all of this, the speeds and what have you, are at the physical, and then the data link layer passes it up. And the Ethernet frames that come in, we talked a little bit about them, but here's a little review. They can be as small as 64 bytes and be a collision frame or maybe a runt frame, which is really too small to be of any use. And it can't be any bigger than 15, 18 bytes. And that would be a jumbo or a baby giant, which means too big to have all the data. But the reason it can be that big is because we can have up to 1,500 bytes of data. So that data, again, you're sending the picture of your cat to your grandmother. Well, that cat's going to get broken down into little 1,500 byte pieces. And, you got pieces of the paw in one frame, some of the whiskers in another frame. And then every little piece of that cat gets framed by a preamble, destination address, and then the source address. And these are MAC addresses, not IP addresses. IP addresses are up at layer 3, and those are buried in the data. So remember, when we talk about layer 2 Ethernet, we're talking about MAC addresses, the physical burned-in addresses on every computer. Now, MAC addresses are hexadecimal, and I've got some support materials on there to learn a little bit about decimal and binary. We could go over a tutorial about how to count, but here's a pretty good idea. Just remember, the hexadecimal doesn't go to 0 to 9, which would be the same as decimal. It goes from 0 to 15. So we use A, B, C, D, E, and F. So sometimes you're looking at decimal, you're looking at hexadecimal because it has some letters mixed in, but other times you don't know. So we use a little hexadecimal signal, the X, to say that this is a binary number instead of a decimal. Pardon me, a hexadecimal number instead of a binary, or maybe even a decimal. So we've talked about binary before in other classes. Counting to 16 in binary should be a skill you have well in hand right now. We've got resources online for you if you do not. But the more you know your binary, the easier it will be. And as we get into IPv6, being able to look at hexadecimal and recognize hexadecimal numbers will help too. So go through those lab packages. And as you can see, after you get to 15, in decimal, when you get to 10, you go over a place and you end up with two numbers. And in binary, it's just you keep jumping bits over. And in hexadecimal, when you get to 15, you start over at 0, 0. All right, so that's 16, 17, 18, 19, 20, the 15, the 16 plus the 4. So hexadecimal can be a bit unsettling when you're not used to it. But hexadecimal is a way for computers to store higher numbers with using less memory. And back in the day, that was a huge deal. So that's why we use hexadecimal in computing and not just binary, because you can represent 4 binary bits, as you can see here, pardon me. You can represent, in one hexadecimal bit, you can represent the value of 4 binary bits. So when memory is short supply, hexadecimal comes into play. Now, MAC address is how we know who your computer is. You've probably seen the MAC address on your computer by now. And you've got every device that is web-enabled has a MAC address of some sort. Media access control address, how the computer gets out on the communication media. MAC addresses are broken into two sides. The organization identifier, which is a unique number for the first half, and then the vendor on the second half. So even if the unique identifiers overlapped on the front side, the vendor would be on the back side. But they're 48 bits. They're huge numbers. Memorizing MAC addresses doesn't do any good at all. They're hexadecimal represented out to 48 bits. That's a lot of numbers. And of course, if computers went out to try to find each other's MAC addresses out all over the world, it wouldn't work. But in a local area network, computers can keep track of MAC addresses in what's called a flat scheme, where a local network is just looking for the same for the MAC addresses in a LAN and not out on the internet. So, first 3 bytes have to be the vendor's OUI, and all MAC addresses with the same OUI have to have a value in the last 3 bytes. That's a bit of detail that isn't too common, but you can see the breakdown. The first, if Cisco made it, the first half says Cisco, and then each device has its own number. And when it processes frames, what happened is a frame, all that data that we just talked about, comes in to a computer, and in that frame is the destination address where it's going, and here's the hexadecimal representation of that, and it has a source address where it came from. And then all of that data that got wrapped into that one little area. Now, if it's going to when it goes out onto, say, through a hub or lots of or into a network, the switch doesn't know whose it is, so it floods it out at the beginning to see where it is. And if there's a match, then the computer takes it up and strips off the MAC address and sends it up. But if it's not, then they just get ignored. All right? So the device will just discard its copy of the frame if it doesn't belong to it. So MAC addresses have dashes, or with colons, or sometimes with periods. All right? The most common, if you do an IP config, you'll probably see a colon for every 2 hexadecimal bits. And that's when you have to record it, you usually put it in pairs. Because it's a long number, you don't want to mess it up. And when you do the IP config, you can see physical address. Okay, well, in this case, it's dashes that come out. All right, for the IP config, I'll So these are the hexadecimal. Doesn't matter capital or not capital. All right. Now, MAC addresses become unicast. So a source host, a computer or a printer or somebody who has a message for the rest of the network, if it's for one device on the network, it sends out a unicast to a specific address. So the destination of a certain device, others might hear it, but they'll ignore it, and then the destination device will get it. Now the IP address would be encapsulated inside the data, but the destination address won't get changed. So the IP and MAC addresses are used by the source to send it out because maybe it knows the IP or maybe it just knows the MAC address. But the combination of MAC address and IP address are useful, especially for the router on the network to sort out. And so we resolve to make sure the MAC and the IP address match the same device when communicating. So a broadcast MAC address, notice it's all Fs. All right, that's the highest number. F is the highest bit order, and it's all Fs all the way across, means that that is addressed to everybody on the network, and everybody will look at it. And then a multicast MAC address will be sent to a group. These are special address ranges that go to just a few people out on the web. So you have unicast, multicast, and broadcast. So I'm going to stop here right now, let you absorb that as we move on to the next section.